So hello everyone once again. Welcome to episode 26 of Warsaw.AI meetup. My name is Pavel. I'm the organizer from the Quantum AI Foundation, and I will be your host today. But today this meetup is organized in collaboration with Ghost Day conference. We also have our guests from Poznań, the colleagues, Sebastian and Alex, and Sebastian will be also one of our speakers, and Alex will also tell a few words about the Ghost Day conference. We would also like to thank our partners and sponsors for supporting us. Thank you, Teresa. Thanks for hosting us. For next time, Data Art and No Magic. Yeah, here is a link to the newsletter that we released at Warsaw.AI. So if you would like to stay up to date with the curated AI news, feel free to subscribe. And yeah, before I go to the agenda, I also wanted to mention about three other AI-related initiatives that we organize. So some of you might remember that in October last year, we announced the competition for the best diploma thesis, bachelor engineering and master thesis on AI, the best thesis in Poland. And soon we'll announce the results, finally. And we are also planning to have something like the awards gala here in Allegro as well on May 6th. So you can save the date. And there will be also presentations of the best thesis. Last time in January, I also mentioned that we are going to organize two new events. One is AI Intern, so it's something like a matchmaking program for online internships in AI. It seems that we are leaning toward research internships, but we'll see. We're going to announce this program probably at the end of April or beginning of May. And in autumn this year, we would like to host our first on-site hackathon, AI Hackathon, Warsaw AI Hacks, Warsaw AI Hackathon. Yeah, if you are interested in any of these initiatives, feel free to talk to us during the after party and networking part. Yes, so indeed, there will be the after party after the talks, but before that, Sebastian Cygert from NASK will tell about AI outside the comfort zone. Then, as I mentioned, Sebastian Chwilczyński will tell about coding agents, a crash course, but there will be also a brief introduction and presentation of the Ghost conference. And finally, Andrzej Kucik will tell about small object detection in satellite SAR images. So we hope that you will stay with us for the after party and have fun. I wish you a good meetup. And Sebastian, if you are ready, we can start.
Okay, thank you. Hi, everyone. Yeah, so the title of this presentation is Outside AI Outside the Comfort Zone. So what do I mean by that? So the machine learning models are usually trained under this IID assumption, which what it really means is that basically during testing, you expect your data to follow the training distribution. And then, of course, outside the comfort zone for machine learning models is the situation when the data doesn't follow the training distribution, which is quite often the case if you are working with some real-world deployments. So I have worked on some products, and like most of the time we have spent during development of those models, we're taking care of the situations which were not part of the training data. So the out of distribution setting, so the OOD scenario. And then we have a scaling paradigm, which is dominating paradigm in machine learning, which says that you will get better models with larger data and larger models, basically. And what it really means that by scaling hypothesis is that we are getting rid of this problem of OOD, because now everything is in our distribution. So we don't have this problem anymore. And so in this presentation, I will start with briefly summarizing the recent progress in AI we have thanks to this scaling paradigm. Then I will talk about things in AI for which there was not much progress over the last few years. And then I will go to the big question, which is like, is scaling all you need in the real world? So the recent progress is mainly due to the availability of foundation models. So those are rather big models which were trained on huge volumes of data. So to give you some perspective, right, the largest language models are estimated to be trained on around 1 trillion of tokens. So if you take human to read this data, it will be around 6,000 years. So it's rather big amounts of data. But then the outcome is that you can take this foundation model and adapt this model to your target downstream task, like information extraction, chat capabilities, and then you can adapt this model with reasonable amounts of data. Okay, and the results are amazing, right? So we now have this chat models, we have great image code generation, speech generation. So for example, I was working on voice cloning in Alexa 2022, and I think like what is now possible is absolutely amazing. So the development is really outstanding. We have AI agents that can produce research papers. It turns out that we can have AI that can be even more empathic. So it's not only about being smarter, but also being more human. So this is also very interesting. And then obviously there's robotics, for which maybe there was not much progress, but the hope is that it will also get there. And however, there are also some areas in machine learning for which there was not much progress. So this is what I would like to talk next. So one first thing I want to mention is this out-of-distribution robustness. So making sure that the models work well if the test data doesn't follow the training distribution. So the most famous example, which you are probably familiar with, are the adversarial examples. Okay, so basically in the first column you can see the original images, and in the last column you can see the adversarial examples. So basically those images are basically the same for human eye. Those are only different by few pixels, but they are totally different for the machine, right? So the model can predict the images in the last column as like can predict the bus as a cat or dog or anything you want. And it's very easy to generate those kind of examples, and it's how it is, right? So this is the paper from iClear 2014. So what I want to mention is that this is an area for which, for example, there was not much progress. So even with the current bigger models, transformers trained on huge volumes of data, they are slightly better, but it's still very easy to generate those kind of examples that will look exactly the same for a human, but will produce very different prediction for a model. And the other thing is out-of-distribution generalization. So this is the famous CLIP paper from 2021. And here they show the generalization of models. So basically they show that they can get a model that will not only recognize images in standard ImageNet benchmark, but also on this kind of domain shifts. So this is the first one is the ImageNet, so the IID assumption, and the others are images which are data sets which are meant to measure the out-of-distribution robustness. So for example, bananas as a sketches from a totally different domain. And what they claim in this paper is that CLIP model is much more robust to distribution shifts. So this is what they show in this table, where they compare with a standard resonant model, show that those models are exactly the same in data distribution. However, they show that their model is much better on out-of-distribution scenarios. So the standard model, right, when it works for 76%, when recognizing sketches, only works at 25%, and the CLIP model is much more better. So the claim is that the model is much more robust, and the results are super impressive. So this was the time when I was finishing my PhD. So maybe I have managed to improve those results by like 3 or 4%, but they have done it for like massively. So this was kind of depressing for me. However, then the question is it better because there is the new training objective? So this is the language image contrastive pre-training, or maybe it's because of this new data set. So they have trained this model using Lion data set, which was just released a few months earlier, and it's a huge data set on which they have used to train their models. And then it turns out, and it also takes around 3 years to realize that there is a significant data leakage. So what you can see in the first column, those are the kind of images you are using for evaluating the robustness. And then in the rows, you can see the images from the ImageNet training data and from the Lion training data. And what you can see here is the obvious data leakage for the Lion data set. So basically, the claim here is that that clip is much more robust to distribution shift is not really the case, because there is no distribution shift in the scenario, right? So, and also one interesting thing is that it took around 3 years to realize this, because the data sets are rather big. So I want to say is that clip is still a better model. If you are developing some application, it's probably better to use clip, but it's not because of better generalization, but because of a better data coverage you have in your training data. And then, so this is paper from this year. I think it will be presented at iClear, following the previous paper where they have designed new test for out of distribution generalization. And here basically they show that there is no clear difference between images trained on ImageNet and on this clip data set. So the ImageNet are the red dots, and the clip models are in blue. And basically there is no significant difference with regard to generalization to this out of distribution scenarios. So that's what I call the illusion of progress on this slide. So this was one thing about out of distribution prediction, and the other thing which is also connected is uncertainty estimation, and this is another thing for which there was not much progress. So basically the AI models can be very confident in the wrong predictions. So basically those kind of adversarial examples, you can generate such examples that the model will be not only wrong, but will be also very confident. So it will say that, for example, this image is 99% cat or dog. So basically, this is the models can be very high confident and also very wrong at the same time. And I think similar situation is happening in language models, which is called hallucinations. So basically, if you ask difficult question to the model, it can start with generating few words, and then after that, it's very easy for the model to generate coherent sentence because LLMs are great language models, even though the sentence will not be true. Right, so this goes me to the problem of hallucinations. So I have a question for you. What time is on the watch? And the hint is that's obviously not the correct time. And the other hint is that it doesn't matter what's time on the watch. The answer will be always the same. Maybe someone knows that. Exactly. Right. So if you Google watches online, you will see that all of the watches, they show the same time or very similar. So basically, someone a few years ago thought that it's actually nice to display watches in when the arrows are like split like this. So basically, most watches show such time. So this is the answer that it's 10 past time, which is not really the case. So those are the hallucinations on images, and also there are many examples of hallucinations in language. So this is quite famous one. Actually, I think it will be fixed at some point, but it's not yet. But it's known for at least 1 year. So basically, you can ask the model what was the first elephant to swam through the English Channel, and then you get answer that there was some elephant in 1950 as a part of circus presentation. And then you can ask more follow-up questions. For example, here I am saying that, okay, this probably is not possible. So then the model realized that, okay, it's probably not true. So what I want to say is that this will be fixed at some point, but either through using instruction fine-tuning or using retrieval augmented generation. But basically the mechanism remains, so basically there is no way for a model to know what it doesn't know. So that's the point I want to make in here. And then we have another problem related to forgetting. So this is something that I am interested from the research perspective. So basically, imagine that you have, let's say, a visual medical imaging model, and you have collected some samples for to detect COVID images, and then you want to fine-tune your model on these COVID images. What will happen, and as a result, that the model will also forget some of the knowledge it had about other diseases. So basically, during fine-tuning, you have to be usually careful if you have a big model that was pre-trained on huge volumes of data. And we also have are working on this at NASK. So this is a figure from Maciek Hrabąszcz and his paper at which he will present at iClear workshop this year, when we are working on safety fine-tuning of language models. So basically avoiding toxic content generation. And what Maciek is showing here is that there's the figure, and we have this on the x-axis general model capabilities, and on the y-axis is the safety score. So the higher the better. And what Maciek is showing is that this is the pre-trained model, this is the fine-tuned model, is that basically fine-tuning the model for safety. We are improving the safety, but we are also like decreasing the general model capabilities. So this is basically the problem of catastrophic forgetting, which is also studied in continual learning. And what I think is interesting here is that this problem is true, even though the models, they are over-parameterized. So they have enough parameters to learn that kind of knowledge, but still the effect is happening, which goes me to the last problem I want to mention regarding memorization. So basically, it turns out there's a significant memorization happening in language models and the vision models. So this is me asking Plume model for the Pantadeusz invocation, and I am asking Plume model in particular because it's not using RAG yet. So you can ask the same question for a ChatGPT, you will get the same answer, but here it's very clear because it's just pure language model, and you get the full invocation, right? So I find this result very interesting, that there is a lot of encoded knowledge in models, which is like probably you wouldn't expect this to be there. And then you can do a very similar thing for the image models. So this on the left one is training set, and on the right the query, the answer you get from querying the model. It's not happening for all of the data, but for many samples which are not that, let's say, popular, you will get such a result. So then going to the final part is scaling all you need. So let me briefly summarize what I talked about, right? So we have this amazing progress with AI due to the scaling paradigm. However, there are still many connected problems like OOD performance, hallucinations, uncertainty estimation, and forgetting. And I think what is important to realize is that despite those capabilities, the AI models, they solve the problems very different way than human. It's mostly by compression and enormous amounts of data into the model, and then interpolation within this training distribution. And going back to this slide, when I talk about IID assumption, so even with the IID assumption, and even if we get the infinite data, which is probably not possible, but even if you get there, it still assumes that the world doesn't change. And it's not really the case, because you have many different situations when the world is constantly changing, and it's full of unexpected or rare situations. And especially if you're working in robotics and perhaps in medicine, there are many novel situations. So I think that scaling probably will not solve that kind of problems, but for sure, from the engineering perspective, it will still allow for the significant progress. The problem is how close you need to get to the 100% accuracy. So the full autonomous driving probably will still take more time than expected. And so I don't have the answer to the question like is scaling all in it, but I want to, let's say, ask another question, which I think is very interesting from the research perspective, is that what will maybe work better in the future? And I will answer this question by referencing the famous paper by Alan Turing from 1950, which is now 75 years old. This is the famous paper where he has introduced the imitation game. And basically what he's saying there is that instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child, right? So this paper is really, really great, so I recommend this reading. But to summarize, I think that we have now built amazing models, and maybe it's time for to think how the models can improve themselves instead of us constantly trying to improve those models. So this summarizes my talk. Just one thing to mention is that we are building AI safety team within the NASK, which is research and product oriented, but there is still enough space for research. So if you are interested, you can also check those links. Thank you.
Okay, thanks. Thank you, Sebastian. So now it's time for questions. Do we have any questions, Sebastian? Okay.
Thank you so much. Thanks, Sebastian, for a great talk. Very interesting stuff. So I have a question about RAG systems within the context of image recognition. So I've been working with RAG systems for LLMs, but I'm not sure how RAG would work with image recognition. Would the model check that the dog really looks like that picture if it hallucinates a dog instead of an ostrich? Or how would a RAG system work in that case?
Okay, so yeah, in this case, when I mentioned that RAG will fix that, I meant that RAG will fix the hallucinations in the language model. The question is how it would fix this one, right? So it's probably not easy, right? Because the model doesn't understand really that it's meant to execute, like understand the content of a watch. So yeah, this one might not be easy. And I think also, like if you refer to adversarial examples, it's probably also not that easy to fix somewhere there, because adversarial examples, just models don't work good for those. But they assume that you have access to the model, which is not usually not the case. They are mostly like research interesting thing.
Sorry, one more question about adversarial examples. Is there any specific thing that throws the model off, like a color or a pixel position somewhere, or is there any pattern to that, or is it random?
Okay, yeah, I don't have this on this presentation, but basically it turns out the models, they recognize images using high frequency, very small patterns. So for example, you can imagine like if you had like a peacock, like you get some pixels with interesting colors. So what you can do, for example, you can generate adversarial examples starting from a random image, from a random noise, and then you will see also this kind of colorful pixels. So those are kind of the patterns that the models are looking for. So this is what is happening in those kind of images. So there are some patterns, but also the thing is that those images are kind of out of distribution for the model. And usually they're like, if you have some decision boundary, the adversarial examples are like this. So basically you don't have to make a big change to change the prediction. Thank you.
Right, thank you. I have a question about the last slide, which was very inspiring, but I was thinking if maybe reinforcement learning isn't like that we teach machines how to learn themselves. So yeah, I just wanted to ask you on your view. Is the reinforcement learning the thing, or?
Yeah, it's also the open question. So there are many problems with adapting models. If you let the models to adapt themselves, one of those is forgetting, which I mentioned. So you still need a lot of data. And yeah, I mean, it might be reinforcement learning, but it's more like research. So it's really far away from getting anything to work. But if you like let the model update itself, probably the objective will be like from reinforcement learning. So there is no like clear supervision there, right? So the objective must be somehow as a reward.
Maybe just about building correct environment and not about algorithms and anything. Maybe we have it, but yeah. Thank you.
Thank you.
All right, let's thank Sebastian once again. Thank you.
Thank you.
And it's time for our second speaker, or speakers actually, Alex and Sebastian.
Okay, thank you for having us first. So yeah, this talk will be about coding agents, but before that, let me introduce you ourselves. Yeah, so we are a machine learning science club from Poznań. We are like actively working like about 10 years or so, and we have a lot of members right now and a lot of sections, and we are like intro to ML, so it's for people that just starting with machine learning. It's more theoretical sections about quantum computing and something from practitioners. And we also have a separate team that is now very large, which Alex will talk you about, and it's about, yeah, Alex will tell you.
Yes, thank you, Sebastian. So I'm Alex, and I'm in the Ghost Day organizing team. And Ghost Day is one of the biggest applied machine learning conferences in Poland. And this will be our 6th edition. And we're constantly on the rise. We meet every year at our university, Poznań University of Technology. And here's just a showcase of who you can see this May in Poznań. So, for example, one of the machine learning celebrities, Max Welling, but also Baptiste from Mistral will also appear to talk about coding agents, just like Sebastian here today. But from other subjects, Andrew from GraphCore will talk about AI chips, and Maya from Meta will discuss graph neural networks. So there will be plenty of different subjects, and actually about 30 presentations, lots of posters, and also an after party at a jazz club where actually we will get to hear Sebastian and his band play. So there's a lot happening, and I encourage you to join us. As I said, we're on the rise, so there's already 500 participants signed up for this edition. That's why the first pool of tickets has already run out. There's only late registration tickets available on the webpage. However, for the participants of this event, we've prepared a special promo code where you can get those tickets for the price of the previous pool. But however, you have to be quick because it only works today. That's why you have to be quick. And so we encourage you to join us in Poznań. That's 9th, 10th May. But if you don't want to join us, then I guess you can take our stickers, which we have left at the table at the entrance. And yes, thank you for having us here. Thank you, Pavel, for organizing this event with us. And I give the stage back to Sebastian.
Thank you. Yes, so cool conference, cool concert. You are more than welcome. All right, so probably you know GitHub Copilot. It emerged quite a lot of time. I hope that you are using it. It's pretty cool, but a lot of change from this time, and we could easily create a game of guessing what this AI coding tool is. So this talk will assume that you know little about coding agents, but I will assume that you know something about programming and you are programming. And we'll start by introducing coding agents, then we will move to the benchmark because it is very important to know what works and what's not and how to evaluate that, and this is definitely not an easy thing to do. And then as the last part, we will consider like tools, use cases, and different trends in research right now. All right, so I will start by showing you examples what coding agents do. And I will start with the one that is probably known to you, which is code autocompletion, which is like not even a recent thing. It's like 20 years ago, people started trying to do this. So first example is inline completion. So I'm writing an endpoint and I have a completion in one line, and the other one is multi-line completion. So these are from developer perspective, from engineer that actually codes it, completely different things. So this is one thing that coding agents can do. The another one, which is pretty new one, and this is being researched recently very much, it's next action prediction. This is a little bit more interesting. So let's say I have a function, and now I decide, okay, I have list of string as an argument, and now I want to make it union. So in Python, it basically means that this argument can be either a list of string or string. Yeah, Python is now becoming typing language, which is quite funny. And as you can see on the bottom, there's a pop-up that a tool found out that I basically changed something, and it is suggesting me you should change something in other place in code. And I'm accepting it, and it figure out, okay, so you need to import union. And this is pretty cool because research is now working on how to do it over the entire code base. So you change, for example, a type of a variable, and now it tries to find out all the places you probably should modify your code. And it's very, very direct, not changing like everything, but just the thing you need. But it's not that good because it introduced bug here actually. Like it didn't found out that I introduced bug. If you see, I'm using enumerate over ordered steps, and if you know Python a little bit, if the ordered steps will be string, it will enumerate over character by character. So unfortunately, it didn't found out that I should also add if statement. If ordered step is string, I should change it to the list. So this is pretty cool. I will be talking about this more. Next thing that developers mention pretty often is that they want to analyze big code bases, like 3,000 files or more. And this is also being researched because a lot of tools didn't work well on that. So simple question, I have like 10,000 files code base, and I want to learn which code elements utilizes Loguru, which is basically just logging library. And as a result, a tool results me all files. As you can see on the top, you have the name of the file and pretty just when these loggers were used. So this is like a search, but it also explained to me, okay, it was used there and there. So this is another dimension, like searching over the big code base. The next one, and probably the most exciting recently, like there's a lot of hype about this, are agentic behaviors. So basically, I want the agent, that tool, to do everything for myself. And I'm just prompting it, write an application in Python Flash. This is intentional, I will tell you in a second, and test it. And the tool asks me, I want to run this command in the terminal. I need to allow it. Then it tells me I want to create those files. So it creates those files automatically. And then current tools can even test it like interactively. It ran the application and opened it in the browser and even wanted to click on it, like in the elements. And the elements give the feedback and it goes on. And the important fact is that I asked about Python Flash, and it assumed automatically that I meant Python Flask because this is a very popular library. And what if I really meant the Python Flash library? Yeah, so LLMs currently cannot, as Sebastian mentioned, are very certain about different things. So this is definitely a drawback. All right? So let's take a look at this summarizing slide for a second. Yeah, so these are dimensions that are being developed and different like types of tasks these agents should solve. And under the hood, this is just basically asking LLMs to do something. Yeah, LLMs become pretty good at doing stuff. So under the hood, it takes everything it can. Like takes your what files you have, what is the content of this file, takes what problems the ID is returning, takes the screenshots from the application, the errors, and in a smart way, because if like very early coding agents were just taking it blindly and putting it to LLM, now it's a little bit more smarter, but it filtered this context, put this to the LLM, and LLM gives something back, the updated code, and maybe some request, okay, I need this and that. And again, the loop goes over and over. So basically, all these tools works in simplified way like that. And if you want to improve, those tools, the all hustle is basically around two like building blocks. LLMs. So first, we want them to be accurate and big and powerful, but also quick. And for some tasks, we can wait a long time. But if we get back to this auto-completion, like if we code, we expect this auto-completion to like pop up immediately, like within milliseconds. So now there is a lot of trade-offing and a lot of cool research stuff that people are doing. So it's not that trivial. And with the context building, if we have 10,000 of files, like we need to also build in a smart way, because we can put everything to the LLM, but from a user perspective, it is very expensive. Like putting 10,000 files into the context, it will cost a few dollars. And yeah, either user pays for it or we as a company pays for it. And it's not the best case from the perspective of both. All right. So this will conclude this first part, and to move smoothly to the benchmark part. I like Reddit, reading about LLMs on Reddit, because people are very active there. And one guy, basically for 30 days, let LLM solve his real production bugs. So he wrote an application that when a bug was put in the GitHub issue, the application automatically solved it and put the pull request. It was a TypeScript, so web development, and out of 21 problems, 12 solved immediately, 6 were a good starting point, and 3 not even close. The price tag was about $10, but he told that he built this application for much longer time that it would take to fix these bugs. But still, if you could just use this application, this would be pretty cool, because for $10, you would save some time. Yes, so this will introduce us to the benchmarks, which basically all coding benchmarks work in a way that guy tested the LLM, the coding agent. Because most benchmarks were that, okay, we have issue, we have code base, and we give it to the LLM. LLM generates response, and the response is now a pull request. And we check if after this pull request, all unit tests pass. And most of the coding benchmarks are created in that way. And every company is basically saying that we are the best now and we are scoring the best on this benchmark. And one of the examples is SVE Bench, which was pretty popular, and now it got a verified version, which is allegedly better. But yeah, also Sebastian mentioned it took 3 years to figure out that the benchmark is bad, so I have similar example. There is a paper that basically found that the benchmark was contaminated. The first thing is that it only comprises of Python repositories. So this is like, not everyone writes Python. I know a lot of people write Python, but not everyone. And also, like 1/3 of task has a link inside, which is shown on the image. So in the issue description, basically there was written how to solve the task. So LLM could just easily, take it and put it. And the rest third of these problems basically had weak tests. So the solution was either incomplete or completely wrong, but whatever LLM did, the tests were accepting it. Yep, so people are kind of depressed about this now. And you know, the Gotthard's laws say that when something becomes a target, it's not a good measure anymore. So every company is benchmarking stuff basically. So when you see that company is releasing benchmark, it's very likely that you benchmarked it. So what to trust? I like doing own vibe checks because it doesn't take that much time, and you can, like, you know what you are doing in your work, so you can ask LLM stuff, and when you find challenging problem, just copy it. And when a new exciting LLM is released, you can just, you know, ask it those questions. And when there was a big thing when Qwen QEQ 32 billion was released, it was a reasoning model and people were very hyped. But when I just, you know, open it and ask it a simple question, it was this reasoning model, so it kind of reasons and has very long chain of thoughts. And I ask it simple question, you know, how many air does the strawberry have? The word strawberry has. And it was like, okay, probably the word strawberry has 3 airs, but am I sure? And like for 10 iteration, it was going over and over because it's reasoning model. It should reason, but it basically was producing all the time. It was making sure that strawberry for sure has 3 airs. So I was not impressed. Next, there's language models arena, and I really, the arenas are pretty cool because it's not like company did some benchmark, but new LLM is released, and arena work in a way that you have 2 columns. You ask a prompt, and you have 2 answers from 2 different LLMs. You don't know who is who, and you vote for the better one. And the LLMs that get better scores are getting basically higher in these arenas. And this is, the bad thing is that it's average over like 10,000 people. So for your specific use case, it might still not be the best. Yeah, as I said, I like reading Reddit because it is a very dynamic field now, and you know, it's pretty hard to be on track. And on Reddit, when something big happens, you can quickly know that, and the excitement from people, and that's pretty cool that there are people on Reddit actually. Regarding benchmarks, I like this either polyglot if you really want that one, because I don't see many companies trying to using it. So that's, for me, it's a good benchmark because it's not being benchmarked. All right. And now we are moving slowly to the last part, the research tools and so on. So big, I think, change is happening regarding the evaluation of the agenting and especially coding systems. Because for now, they were evaluated that you have a task, you have k chances to solve this task, and if you solved it once correctly, it's good. So like imagine having a bug fix to solve, and you give LM 3 chances, and one of those chances is good. But it's like, okay, I need to evaluate now which of these approaches of the LLM really fix the bug. So there's a switch to pass, I don't know, caret, K, I don't know how to read that really. So the LLMs must succeed each time. So it's reliable systems. So it's a big switch, and I think it's a good one. Right, now before introducing more these concepts, a few more, let's take a look at what coding tools are available, because I told you what these coding agents can do, but this can be implemented in different tools. So you can have IDE that is AI centric, and as an example Z, I will show more examples at the end, but I will mention these tools later. They're extensions to existing IDEs. So you can go to VS Code and have the extension. CLI-based tools that you need to run in terminal, and apps oriented to non-coders, which I, for now, skip. So, yeah, the biggest research trend and the biggest opportunity for now I see are these next action predictions, because other functionalities are implemented in like all those tools I know, but this is just implemented into Z in augment code, and there are actually many research questions here. So first, how to even make it work, and Z did it in a really rudimentary way, just fine-tuning DPO, and how to make it quick, speculative decoding, but yeah, making LLMs quicker is still a big thing. And Augment Code, another company, they wanted to make it over entire code base. So first, they asked the questions how to find the user intent. So when to know that users should actually change a lot of stuff. This is pretty challenging, and this must happen every time user writes something. So it's pretty also latency must be low, and it must work over the entire code base. So where to modify, like when we have 3,000 files, we need to find all potential places for modification. So this is pretty challenging retrieval task, and they are not using LLM for that. And how to modify, how to teach LLM to, because LLM on the input is getting the entire file, and it just must return this modification. So this is pretty challenging. So there are like many open questions on this coding agent stuff. Also, reinforcement learning is now very popular. So what people are trying to do is just to basically take all pull requests possible from the GitHub, and automatically with reinforcement learning algorithms, when you just need to, like you kind of just compare the pull request that was merged with what LLM produced, and if this is close enough, you give a reward to the model. So you just need to scrape entire GitHub, all pull requests ever created, and potentially you can train a good model automatically without any labeling. Yeah, so this is about research. Cool non-trivial stuff for me that not many people are writing about. There are command line tools like Aider, and basically you can automate stuff with them. There's a good case study when guy need to do gigantic refactor, but it was independent from all the files, and he just, wrote this Aider and some, comment to it, and go over all files and fix it. Like these tools that are in the IDEs does not support that, so that's pretty cool. And yeah, a more extensive list of AI coding tools. But as we are running out of time, I will just, print the whole summary of this basically slides. And thank you very much.
Thanks, Sebastian, and thanks, Alex. Do we have questions?
Thanks so much for a great presentation. Regarding your slide where we saw that they are trying to scrape all GitHub and feed it to the LLMs and to learn better, when AI agents will write more and more code on GitHub will be written by AI agents. So is it a case that the data will be diluted, and all the data will be synthetic basically? And do you think there will be a drop in quality?
Yes, that's an issue. I probably seen a paper on that people are like, it could be described as a dead internet theory. Yes, basically that everything is generated by bots, and yeah, that's an issue that probably it will be of lower quality. But if you look at the research, a lot of basically papers assume this works. So there was pretty recent research about, it was called TAU, and it was about fine-tuning LLMs without any labels. And it basically worked in a way that you have just input, and LLMs produce other output. Other LLMs basically says if this output is good or not, and like this is the reward to that model. So now it's very, LLMs evaluate LLMs if they work correctly. LLMs are trained on LLMs generated data. Yeah. Is it good? I don't know. Like the models are still getting better, so somehow this works, but yeah, it may plateau due to that.
All right. Yes.
I wanted to ask your thoughts on the subject because lastly I work a bit with agents and with the LLMs. That the point right now is just to choose the right thing to work on with LLMs. That the point is right environment. That we just need the task in which we don't need high precision. I mean, like 100% precision. So like generally on this slide you showed that like 3K, yes, it was 97%, but the point is that we have to allow our model to make mistakes. So I think that like firstly it will start to work in the task when this, I don't know, not 100 precision is needed. I mean,
Yeah, that's a good point. Like the LLMs are good for tasks that we don't need them to be reliable. Yeah, they can. Yeah, that's a good point. But yeah, is the coding such a task? Do you think?
I mean, to be honest, I'm not sure. I wanted to ask what is your opinion on this? I mean,
Yeah, I agree that LLMs are much better than at being like at accepting not perfect solution. This is pretty good, but the thing is that in many environments we actually need a reliable system. For example, okay, when you chat with something, it may make mistake, but when you allow it pushing pull requests on production, we want it to be pretty reliable. And yeah, most of the use cases I know, basically, they must be reliable, and that's the thing. What is pushing like investors from being afraid a little bit, because there's a lot of hype, but besides the chatbots, which is the case, they don't have to be very precise, or some RAG systems that they need to just retrieve something and write something back, and it's not like it doesn't have to be reliable. I don't know such systems. Like, if you know, I'm happy to hear about them.
yeah, I mean, it's the same thought I had, that you just have to use them when it's not like 100 precision needed.
Yes, that's yeah, but everyone does it now. Yeah, so maybe we need to make them reliable, and then we are, change the world.
Yeah, I mean, maybe I'm a bit skeptical right now for this vision, but who knows?
Yeah, I would say I'm skeptical too, but yeah.
Thank you very much. That was a great presentation. The title of the presentation is something about agentic, yes, but most of the examples that we have seen are about individual calls to LLMs. So from the agentic system, I would expect that it maybe makes a plan, yes, breaks down the problem into single tasks, then solves those tasks, yes, maybe reflects on the result, then decides on another plan, yes, etc., etc. And are there any examples of such a systems that actually work?
Yes, actually, like this is the simplest agentic like loop, yeah, because agentic is basically what you said. So under the hood, if you just use this maybe C line, okay, maybe I'll show it on this example. So if you give this prompt, at first it will say, okay, so you want me to implement an app in a Python Flask, so I need to do this, 2 this, 3 this, and 4 this. And it's like, okay, I need to do this. And this is like this planning part. Then there's this working with the environment, and in this case, environment is basically IDE that this agent operates in. So it interacts with the environment. So for example, it can run commands in the terminal, it can create files and write to these files, it can open the browser and click in this browser. So this is working with the environment. And the last thing is, okay, it will be here. Yeah, the reflection on stuff. So it is also, reflection can work in the way that, for example, you have an error, and this is kind of reflection. It goes back to the LLM, but also this reasoning models reflect very much over themselves. So LLMs like now are doing it by default, pretty much, the planning part and the reflection part. If you ask LLMs and prompt them correctly, they will create a plan, of course, work with the environment, get the feedback from the environment, which will be in a form of this, for example, exceptions, or when they click on the app, what happens, and improve. And this is of course loop. So yes.
Yes, indeed. I didn't get this example at first try. Thank you.
And this is indeed the most of the tools. Like if you do look at these tools, this cursor, Windsurf, PureEye, Z, C-Line, Augment Code, Codo, Cody, Avant, like almost all of these tools are doing this agentic stuff. Because this is kind of became a default of coding agents, how they behave. Yeah.
Thank you. Thanks for the questions. Sebastian, thanks for answering. Let's give one more round of our applause for our speakers. And it's time for our first speaker, Andrzej Kucik.
So maybe I start with a very brief introduction, some stage setting, and a disclaimer. I'm from Helsing. Helsing is a European defense company that was established to protect European liberal democracies, mainly through building a European strategic autonomy in the defense, AI, and software. So a couple of weeks ago, you might have realized how important is military intelligence and military intelligence satellite data when Ukraine briefly lost access to this data, and that was quite harming for them. Now, Helsing has been supporting Ukraine very firmly from the early days of the war, and that includes also the satellite intelligence analytics, something which is also a subject of this talk. And because of that, I cannot go into too much depth, not to reveal certain operationally sensitive aspects of it. But I hope that despite this, you will find the talk quite interesting. So, small object detection in satellite SAR images. So I'll start with telling you what we mean by small object detection. So here is a satellite SAR image. And like in an interactive way, I would like to ask you if you can see where in this image is a military vehicle. There's one. You've got this beautiful huge screen here, so it shouldn't be too difficult. Apologies to everyone who may be watching this online and having to find it. Does anyone see where is the military vehicle? Yeah, correct. It's to the right. This is an easy example because it's on the road, so that's where you usually see the vehicles. But you may understand that as far as computer vision is concerned, this is a fairly difficult problem to solve. And this is actually a zoomed in image. I have a short video here, which I hope is going to work, that will show you like the entire process of zooming in and out. So this is the zoom out full SAR image. And I'm going to toggle off and on where the vehicles are. Sorry, I think it's, yeah, I need to play. Yeah. So yeah, I'm talking of the vehicles. That's where they are. Not very clear, so we need to zoom in. And after we zoom in, we see them more clearly. And that's where they are. And I just show you this example in more zoom, right? Sorry. On the, okay. You may need to trust me. That's what we see. So on the left there, oh, sorry, again, we had an example of a military vehicle. On the right, there was a false positive, so something which looks very like military vehicle, and those are usually the problem. So the purpose of this was to show you that the problem is difficult for humans to understand, and even more so for machines. And the next thing I want to talk about is this modality, what I'm actually showing you, what are these images? So what is satellite SAR? So SAR is a type of radar, and radar is an active sensor that uses the electromagnetic spectrum, electromagnetic radiation for imaging. So you send a radio wave, and you receive back some signal, and that tells you about what is out there based on the return rate. You can construct 2D images out of radar by taking into account the differences between when you receive the signal. But the problem is that the further away you are from your target, the lower is the resolution. So putting a radar on a satellite is challenging. To give you an example, to have a 30 centimeter per pixel resolution, which is what we need for this problem, if you put a radar satellite on a low Earth orbit of, let's say, 600 kilometers, you would need an antenna of length 9 kilometers to actually be able to do it, which is not feasible. We cannot do it. So what do we do instead? So antenna length, in other words, is called aperture. We construct a synthetic aperture. So we take a sequence of images as the spacecraft or the aircraft, sometimes it's put on planes, traverses its path, and then we construct out of these images a single image as if it was collected by a very long antenna. So that's why it's called synthetic aperture radar. It has this like sideways look, and its resolution, which is perpendicular to its path, it's called range, and the one is parallel is called the sorry, I lost the word. I don't remember. It's the azimuth, and the return rate of the signal that we get is called the amplitude. So such sensors are often put on airplanes, sometimes on satellites, and they come in different bands. So depending on the wave length of the radar, you get different kind of ground resolution, and also different ways of different rates of penetrating the atmosphere, or even through foliage, or even soil with this lowest frequency rates. What is most commonly used for SAR is the C-band. We are, however, focusing on the X-band because this is the one that gives us the highest ground resolution. Normally from 1 to 3 meters per pixel, but with special imaging mode, you can go to sub 1 meter resolution to 30 or 50 centimeters. Another detail that we need here is about the polarization of SAR. So when you have this plane between your antenna and the Earth, the sine waves or the radio waves that traverse it can be perpendicular with 2 degrees of freedom. They can be either horizontal or vertical. And that can apply to both the emitter and the receiver. So you can have an emitter which emits horizontal wave, and then the receiver senses the vertical waves. And that's how they're called HH, HV, and so on. Now, if you have a perfectly smooth surface, everything is essentially beamed away from you. You don't observe anything. The more rough is the surface, the more you get back from the radar. So everything that appears bright on these images is quite rough. And we have essentially 3 ways of beaming back the signal. One is just you get a surface beam, so we have a rough surface and you receive back the signal. One is the double bounce. So you send a signal, it's bounced once from some surface, bounce back to another one, and then you receive it. This is something very apparent in urban environment where we have a lot of tall buildings, and they may bounce off the walls and the roofs, also with tall vegetation. And the final type is the volume scattering, which is that you send a signal and it's bounced multiple times before you receive it. This is very common with vegetation. For example, if you have a tree and you've sent a radar signal towards it, and before you receive it back, it bounces many times from the leaves. And in that case, there is the highest probability of changing the polarization of the signal. So this is something which we very often see in this mixed polarization setting. But in the urban environment, we receive the biggest amount of scattering from the HH polarization. And this is essentially what we are using. Sometimes they're combined, as you can see on that false color image on the right. So when you see that false color radar images of the Earth, this is how they're combined. So the green is, since it's very sensitive to vegetation, is assigned to HV and VH. VV is very sensitive to the water, so we assign it to blue, and then you've got this almost natural interpretation of this colors. However, this is not always available, and we are only relying on a single polarization satellites with mostly HH polarization. So to finalize this quick introduction of what SAR is, I wanted to talk about why we use it and why it's difficult to use it. So first of all, it's an active sensor. So it doesn't require external illumination. So it doesn't matter whether you try to take the image at night or during the daytime, they look exactly the same. So you can monitor certain areas at night. The second thing is the microwave window. So from about 1 millimeter to 30 centimeters of the light spectrum, light is not, it's not very well absorbed by the atmosphere. You can penetrate through it very well. Which means that we get a very stable geometry. First of all, we don't have any deformation. And the second thing is that it can penetrate through clouds. So even if there's a cloud coverage, we are perfectly capable of seeing what's happening on the ground. So you can have clouds, you can have night, and with SAR, you still see exactly what's happening on the ground. But there are some cons. One is that the coverage is limited. So we cannot put this on geostationary satellites. We have to have a moving spacecraft, and that means that if it moves away, you are no longer able to monitor that area. You need to wait for the satellite to come back or another spacecraft to come into the area. Also, it's an active sensor, so this beaming of radar signal takes a lot of energy, and if you take a lot of pictures, the spacecraft may become unavailable for a while so that it can recharge. And what is relevant for us is the AI ML model availability. And that's a huge con because, you know, most of the computer vision models are trained on images of cats, dogs, and similar. They never get to see radar images, so they don't really understand what they are looking at. Architecture, like the things like invariance in convolutional neural networks are completely unsuitable for this kind of data, the augmentation as well. So it's difficult for AI people, but that changes. And what is related to that is the annotation difficulty. So you've seen these images. They are quite unintuitive to us. And the professional annotators, when they look at it, they don't understand what they're looking at. So they cannot really look at it. And I tell them, please annotate all the military vehicles. And they simply don't know how to do it. So now moving to the problems that we've been trying to solve. So we have this kind of images. There is another example of military vehicles, which I'm going to show you. It's here. And these are all single polarized X-band SAR images. The ground resolution is about 35 centimeters. The entire image is about 23K in resolution, so they're huge images. So we have to chunk them when we do both the training and the inference. And the nominal scenes are about 5 kilometers in size. What we want the network to do is to find the military vehicles. And this is actually quite interesting because in the optical data, you know that military often uses some paintings or some nets that they put on with leaves on the military vehicles to make them impossible to see by the optical imaging sensors, but in radar, you can penetrate through this and the color of the paint doesn't matter, so you can still see them. So this is quite of huge value for the military to be able to do it. And they're quite small, so we need to annotate them only by center points. Putting bounding boxes around them doesn't really make sense. I mean, you can do it, but it's not very helpful. And we have two data sets. One is of the that has been used for supervised setting, which is about 120 train images and 5 and 8 for validation and test. And we also have been kindly given about 1,000 images from commercial provider Capella that we used for self-supervised training. Now, the image availability is a problem. This data is quite expensive. A single SAR image can cost about a couple of thousands of dollars. And then, so you imagine that even these small data sets can cost millions to procure. And then, as I said, labeling them is very challenging because people don't really know how to do it. And they don't have any of the reference data to understand what they're looking at. So how do we approach the problem? With this mixed self-supervised transformer architecture. So we take all these SAR images, we chip them into more digestible size chips. We apply some normalization, which I briefly will talk about in the next slide if I have enough time. And then we process it through a transformer architecture, which is based on a Swin transformer. And in the unsupervised setting, where we do not have the labels, we essentially ask the model to do mask image modeling to reconstruct the scene. And thanks to that, it can actually learn what are the typical patterns of SAR imagery. And in the supervised setting, we ask it to create a segmentation masks for the foreground, which are the military vehicles, and then for the background, which is everything else. Then we convert these segmentation masks into detection points and measure the distance from the desired targets. And we express our results as a F1 score. Because we don't want to miss any detections, but we are also interested in reducing the number of false positives, which can be easily observed here. Now, another problem here is that the positive examples, so the examples where we actually see the vehicles, are very few. And if you have this single pixel of a military vehicle in 23K resolution image, you can see that this creates a lot of data unbalance. So we have to have this adaptive sampler that essentially increases the amount of background and decreases the amount of foreground as we go through the training, so that the network can benefit from seeing, in the supervised setting, from seeing more vehicles at the beginning. So I told you about this normalization step very briefly, that there's 1 or 2 slides about it. Basically, another problem is that SAR data is not normally distributed. So when you do this normalization to either subtract the mean or divide by standard deviation, or you want to just normalize it to 0, 1 range by division, that creates a lot of data which is just zeros. Because it's very close to 0 and has this skewed distribution to the left, which is Rayleigh distribution. Rayleigh distribution is what you have, for example, with complex numbers, when the imaginary and the real component are both normally distributed with 0 mean and the same variance. And if they're not correlated, then their modulus is a Rayleigh distribution. So we have these 4 types of essentially renormalizing the data. They're also used to make it more understandable for humans, because if you don't normalize it, they just all look black. But apparently, this palest example of logarithmic normalization is something that the neural networks like really much. So that's what we use. And to summarize it, these are the metrics that we get. So because we solve it as a segmentation problems, we compare it to 2 segmentation models, so UNet and DeepLab. One of them was pre-trained also on COCO, and one was pre-trained on SAR data from Sentinel satellites. And the best one of them was the UNet pre-trained on SAR data, which gets about 50% of F1 score. But after we deployed the transformer-based network, which was pre-trained on this Capella data set, we managed to boost it by more than 10% of F1 score. And when we also applied this adaptive sampler, reducing the amount of positive samples through the training, that gave us another 10%. And on top of that, when we apply the normalization, we get almost to 80% of F1 score. What does it mean in practice? This is a superhuman ability. As far as I'm concerned, no human can actually beat that score and be able to find all these military vehicles in that data set. So to finish, here's a couple of examples. So here's an example of a cluster of military vehicles. They look different than normal military vehicles because the signal actually bounces from them and they appear brighter. So the supervised model doesn't understand it and treats them as something else. Whereas with SSL, we can actually get these detections quite well. We also have sometimes some artifacts which look like vehicles because we've got this moving spacecraft and it takes a sequence of images. Sometimes like a metal barrier that is attached to the side of the road may look like a sequence of points that supervised models interpret as vehicles. We are able to reduce it in the self-supervised model. And also we reduce a lot of false positives. So here on the top, you have only 2 true targets, whereas on the bottom you can see that the supervised model gets a lot of false positives. And that's all. I hope I'm on time. Thank you.
Thank you. Right, thanks Andrzej. It's time for questions. Yes.
Thanks, great talk. I have a question about latency of this system, like from something happening on the ground to, I would say, analyzing. How long does it take?
Okay, so getting the data from the satellites, the quickest amount of time you can do it is about 4 hours. You cannot go below this. So no commercial provider will give you images in less than 4 hours. We are able to process them like all this huge image in about 40 minutes if it's a standard laptop that is used on the battlefield. So you know, in that case, you cannot really have some GPU cloud computing. This has to be all done offline. And yeah, so we could probably do it in a couple of minutes. With a powerful GPU on a standard laptop, it has to be more.
Thank you so much. Great talk. I assume that a potential countermeasure for this would be an armored vehicle which has a very smooth surface. Is that something, maybe you cannot tell it to us because it's sensitive information, but is there such a thing? Or is it not realistic because of the bouncing effect that you mentioned?
Yeah, I think the bouncing would take this away because it would bounce through all this, you know, perpendicular surface that it has. It's a difficult problem, and that's why you have this, I don't know, stealth planes that most the US is excelling with, that they can build a plane with such a shape that it either absorbs all the radar signal that it receives or it bounces everything away, and that's how it becomes invisible. But that's a very complex technology. And I imagine also a vehicle which, you know, has to be operational. It gets damaged a lot, so it creates a lot of dents that are easily detectable by these models.
Thank you.
Hi, I wanted to ask about how reinforcement learning is used in this domain, because I came across a few papers that where they're using RL models to zoom in on a particular piece of data and then like analyze it more. Can you talk a little bit more about it?
So I know there is some work done in like more classical object detection with bigger objects. So things like aircraft or watercraft vessels. But it's quite different. I haven't seen it in the context of segmentation of very small objects. So I have no knowledge of that.
All right. Oh, there are some other questions.
Yeah. Okay, thanks. I was thinking about this problem, like, have you ever considered using super resolution in such cases, or with such small objects, it's just doesn't make sense because such hallucinations for such small objects. And by the way, how big are these objects as a pixels? How many pixels they have? Thanks.
Yeah, we did consider that. There's a problem with that. And the first one is the thing that you mentioned, which is the hallucinations, which would be a huge problem because, you know, in operational setting, you would essentially create targets which are not there. And those samples look very similar to noise, so it's difficult. Some people work on super resolution with SAR, but there's a lot of hallucinations, or a lot of things which to our eyes looks they look very legit, but when you actually look at the distribution, for example, of the amplitude and so on, it seems that this doesn't make physical sense. So this is a problem. There's also a problem with synthetic data. So some people try to create synthetic SAR because normal SAR is so expensive and difficult to collect. But I haven't seen anything convincing that I would use.
All right, then the last question.
Thank you for the presentation. Very interesting. I was thinking if you cannot answer that question, it's fine. But I was just thinking about that normalization. Since I also work with signal, I have this quasi like theory. An imperfect normalization is better than no normalization. So I was just curious if perhaps first you follow this paradigm of just taking the mean and standard deviation and trying to normalize the samples, and then you basically forwarded that approach to more sophisticated one. Did that bring a significant breakthrough in the results of your models, or was it neglectable?
I think I can answer to that. Basically, we tried all of these 4 normalizations and the standard ML normalization, so just subtracting mean divided by standard deviation, or with the supervised model, so with UNet and DeepLab, didn't make any difference. It was very negligible, so we initially said, okay, there is no point in doing that at all. But when we moved to bigger architectures, to transformers, it actually made difference. So I imagine that it might be also a common case that if you have smaller models and that didn't have a large training data set, maybe it doesn't make a difference, but once you move to a bigger distribution, wider distribution of features, it may make difference.
All right, let's thank Andrzej once again. Thank you. Great, so that was the last talk for today. Thanks for all the presentations and all the questions, all discussions. I hope we will stay with us for the after party and we can officially start the after party. So the food is in the fridge. Yes. As usual, yes. So enjoy, have fun, and we hope you all will stay with us. Thank you.